Welcome to Android Fundamentals. Getting started on Android is straightforward. Simply installing Android Studio and creating a new project is enough to have ticked the Hello World box on your Android resume.
But that's not why we're here. We're also not here to teach you Java, and we're not going to walk you through every API in the Android SDK.
But what we will do is to help you build a real app. We'll dig into the fundamentals of how Android works, its patterns, and best practices.
Our course is deeply rooted in code, but this isn't a copy-paste code lab. We'll teach you the principles you need and help you navigate the hundreds of resources like sample code, documentation, and Stack Overflow that you'll be using in your career as an Android developer.
Getting started is easy, but building something great is harder, which is why we're here.
We'll work right alongside you, and by the end of this course you'll be able to turn your app vision into reality, and you'll build it the right way. So in that spirit of collaboration, we'll begin by telling you a little bit about us and where you'll be seeing us throughout the course. Catherine, why don't you get us started?
Sure. I'm Catherine Kwan, and I'm a developer advocate at Google. I started off by working as an engineer on the Android apps team. I worked there for 3 years on products like Google Play and Google Keep, the note-taking app. I'm continually blown away by what you can build on this platform, and I'm particularly inspired by those apps that can truly improve people's lives. When I meet people, they often tell me about their great app ideas, but then they feel like they don't have the technical skills to actually build it. And that's why I shifted over to developer relations, so I could help people like you really build something great. Throughout this course, I'll be helping you implement your very first app.
My name is Dan Galton. I've been a developer advocate at Google for 4 years, and I've worn a lot of hats here. My goal is to keep us on track to make Sunshine something that had some resemblance to a production quality app. I'll introduce Android design patterns and principles, many of which are often missed by new Android developers. You'll learn to lean on the framework, focusing on what makes your app unique instead of reinventing the wheel.
I'm Redo Meyer, and I've been a developer advocate for Android at Google for 5 years. I started working on Android so long ago that back then there were no devices. All you had to work with were an emulator, a beta SDK, and an almost fanatical devotion to the platform. I'll be joining you from here, my underground Android developer bunker. And my goal isn't to get you up and running as quickly as possible, it's to teach you the context behind the choices we'll make and the best practices you need to really understand how to create great experiences specifically tailored to mobile devices. By the time you finish this course, you'll know more than just how to create yet another app. You'll know how to build great apps that focus on the user.
In this course, we're going to build a weather app called Sunshine. The main screen is a list of this week's forecasts, with an emphasized presentation for today's weather. With just a quick glance, I can decide if today is a stay inside and code day, or if I should code from the park instead. We have icons to indicate conditions like snow, rain, fog, or sunshine. We can scroll through the list to see a long-range forecast. With a click on one of the forecasts, we bring up a detailed view containing the rest of the weathery goodness, which also gives us the ability to share the weather with our friends. We can go to Settings and change the unit of measure, as well as the location. The app can even post system-wide notifications to let us know about weather conditions without even entering the app. So, you might ask, why are we building a weather app? We chose the weather app because it's a simple concept, which touches most of the core APIs we want to teach, and everyone can relate to weather, unless you're in a bunker. By the end of the course, you'll be able to use those APIs and concepts to build your own app for your final project.
Now it's important to remember that we're not here to teach you how to build a weather app. It's not even to teach you all of the Android APIs that we'll use to build it. It's really about retraining your brain to start thinking like a mobile developer, which is really important because at the end of this course, we're going to ask you to build your own final project. We're expecting you to already be familiar with object-oriented programming, and to have experience with Java or a similar language. Personally, I got started with Android after years of Delphi and C# development. As engineers, we're trained to map our experiences in one language or SDK into new ones, looking for patterns and shortcuts so we can get up to speed as quickly as possible. But mobile, and Android in particular, has some fundamental differences that mean some of our experience and intuition will actually make us worse mobile engineers. We like to think of smartphones as computers that fit into our pockets. In a way that's true, but they're computers from the 90s, like this powerhouse I was using nearly 20 years ago. With limited internet connectivity, low-speed CPUs, and limited RAM, on top of which they're all running on batteries. As we go through the course, I'll be returning to each of these key mobile challenges, looking for places where your experience on desktop or server or even other mobile platforms might lead you in the wrong direction. I'll also be back to tell you some stories from the early days of Android. Stories that describe how the Android platform has evolved. And nowhere is that more readily apparent than here at the Android Lawn Sculpture Garden. Join me here at the very heart of Android at the end of this lesson to find out how this sculpture garden of tasty treats also tells the story of Android's history. For now, let's get back to building that weather app. So we'll cross to Dan to take a look at some mocks.
Thanks, Rado. But let's start thinking about Sunshine, meaning our app. I'm not convinced I'm ever going to tire of the obvious puns our app name allows. Remember, as we progress through this course and build this app together, you should be thinking about the app you want to create. There are too many weather apps already, after all. By the end of the course, you'll be ready to tackle the final project, using all your new Android know-how to build your own app.
Thanks, Dan. As mentioned earlier, we'll be using Android Studio throughout this course. It's an IntelliJ-based IDE that is optimized specifically for Android development. It's still in beta development, so your version may look slightly different, but that's okay. The core functionality should still be the same. If you haven't installed it yet, take a moment to do that now, using the detailed instructions provided in the link below. You'll also need to install the support library, and that's also included in the instructions. Note that the SDK is included automatically, so you don't need to install that separately. If you're having difficulties, no worries at all. We totally understand because it can be tricky to get everything set up properly. You can search online for people who have a similar issue, or there's a troubleshooting link included below. If you still need help, you can ask a question in our discussion forum as well. Once you install it, open it, and you can check for updates before proceeding. Check this box when you're done. Once you install Android Studio, you can open it and check for updates before proceeding. Then we can configure Android Studio. Open up the Android SDK Manager to see what tools, platform versions, and components we have installed. At the time of this recording, the Android L platform is available, but it's still in developer preview mode. That means it's subject to change until the official release. And you can't upload your app to Google Play if it's targeting this L platform version. Hence, we want to use the latest stable platform version, which is KitKat or API level 19. API level 20 is for Android Wear or watches, and not for phones or tablets. Deselect all the other packages and just choose the ones for API level 19. We want the SDK as well as the system images for the emulator. We also want the Android support library for backwards compatibility. For the most up-to-date version of all the packages you need to install, check the link below. Otherwise, continue with installing the packages. Accept the license and then install. Then we can click and create a new project. In the project wizard, we set the app name to be Sunshine. Then we provide a corresponding package name. For distribution purposes, the package name should be globally unique across packages installed on Android. To avoid conflicts, you can use the reverse of the internet domain that you own. This follows the Java package naming conventions. Note that we're also using the com.example namespace for our Sunshine app because it's a sample, but you cannot publish an app on Google Play that uses this namespace. Usually leaving the default package name that's suggested is fine. However, this class was originally filmed with an older version of Android Studio, which added the app module at the end of the package name. So go ahead and make this change now if you want your code to match the rest of the code in the course. Then we choose our project location and we hit Next. Now we need to choose our minimum SDK version. In previous versions of Android Studio, you would also have to select the target SDK. But now the project wizard automatically sets the target SDK to be the latest version. Even though target SDK is already selected for you, it's important to know the distinction between min and target SDK.
Android 1.0 launched in 2008, and in just the 6 years since then, there has been 11 new major platform releases. On the Android developer site, we show the relative number of active Android devices running a given platform version in this pie chart, because pie charts are awesome. For our purposes though, you're really better off looking at this as a histogram. If you squint, you can almost see a vaguely bell-shaped curve. With the oldest releases here at the left, their popularity dropping off as devices are upgraded or replaced. The largest proportion of devices are here in the middle, representing devices about 2 years old. And the newest platforms, gaining popularity as new phones are released or upgrades go out, are here on the right. So with that in mind, the Min SDK acts as your low-pass filter. Google Play won't show your app on devices running a platform version lower than this minimum SDK version. So why not just set the Min SDK to 1 and support everyone? Generally, you'll want to target as many users as you can, but there's a cost associated with supporting some of these older versions. Things like creating different execution paths around deprecated or update APIs, or presenting a different UX to devices with different features. So you need to balance the opportunity of expanding your audience with the cost of supporting those new users. Also, remember that each release introduced with it new APIs and hardware support. So it may not make sense to make your app available to devices that don't support your minimum feature set. By comparison, the Target SDK is not a high-pass filter. It's used only to declare which platform version you've tested on. An app targeted to a certain API will continue to be forward compatible on future releases. The platform uses the Target SDK values in case a future platform makes a significant change to expected behavior. This ensures your app doesn't break when a user's phone gets upgraded. If you're developing a new app, there's really no reason to target anything but the latest Android version. And once your app has been released, make it a point to update your Target SDK and test as soon as possible when new platform releases roll out, so you can take advantage of every new platform optimization and improvement it has to offer. The distribution and latest version of Android changes frequently, but based on this graph, which version of Android should be the Target SDK to provide the best experience on the largest number of devices? That's right. While setting Froyo as our minimum SDK would allow us to support 100% of devices, it's the wrong choice for our Target SDK. To ensure the best experience for users on all phones, including the newest KitKat releases, we need to set our Target SDK to the latest build, which is KitKat.
Thanks, Rado, for telling us about the importance of proper dessert selection. Let's choose our dessert now. At the current time, choosing gingerbread covers 99% of the devices active on the Google Play Store. It's also the cutoff for using Google Play services for things like maps and location and the Android support library. The support library package offers an implementation of UI features that were added in later releases but now can be used on older versions of the platform like Gingerbread. We picked the latest version of Gingerbread at API level 10 because it contains bug fixes that API level 9 doesn't have. Then we go ahead and click Next. We're presented with a list of templates that we can choose from in order to create our new app. We're going to pick the blank activity with fragment template. For background context, an activity serves as a presentation layer for our UI, and the fragment within it represents a behavior or portion of the screen. Go ahead and click Next. We call our activity main activity, and the layout comes from the activity_main XML file. In a similar fashion, the fragments layout comes from the fragment_main XML file. Then we go ahead and hit Finish. You should have your newly created Sunshine app with the files on the left here. Make sure you wait for the Gradle build to finish. If you still see errors, you can check the guide in the instructor notes below on how to troubleshoot. As a tip, you can check your Min and Target SDK versions in the build.gradle file located under the app's source folder. We want the compile SDK version and the Target SDK version to point to the latest stable version of the platform. In this case, it's 19 and not L. Once you have no errors, we can add a custom app icon that'll be more fitting for our weather app. Right-click on the app folder and go to New Image Asset. Download the icon that we provide in a link below, then go ahead and find that icon. And here you can see a preview of our temporary app icon. We're going to get a better one in Lesson 5. Then go ahead and click Next and Finish. And the new icon shows up in the drawable folders. Go ahead and try it yourself. Make sure you're using the same settings as we have by checking the link below. Click here when you're done. I know you're excited to run the app, and I'm going to show you how to do it without a physical device because we'll be using the emulator. But first, we need to install one more component from the Android SDK Manager. Click on this button to open up the Android SDK Manager. Scroll to the bottom of the list to find Haxum. It stands for Hardware Accelerated Execution Manager, and it will speed up our emulator. So go ahead and deselect the other packages and just install this one. Accept the license and then continue. We have to do one more step after this to install HackSum. I'll show you the remaining steps on a Mac, but for the other platforms you can check the link below. First, find Android Studio under the Applications folder, and then hit Show Package Contents. Then in the SDK folder, there'll be an Extras folder containing an Intel folder with the HackSum folder. Then we click on the DMG file, open it up, and then continue. Step through this installer and the default values are fine. Once the installation is complete, you can close all the windows. Now for the moment you've been waiting for, let's run the app by clicking on this button. It will prompt us to choose a device. Without a physical device, we can use the emulator, which is included in the Android SDK. Currently, it says that there are no Android virtual devices available. So let's open up the AVD manager to create one. Then click New. By creating an AVD, we can configure an emulated device with the Android platform version that we want to test on, as well as hardware options. For our case, we're going to emulate a Nexus 5 virtual device. The defaults are fine for now, so we're going to hit OK. Then we see that our AVD was created successfully. We can close the AVD manager, and when we go back to the device chooser dialog, we'll see that Nexus 5 is an option. Then we can hit OK to launch the app. When it loads up, we see our Sunshine app with the words Hello World. Keep in mind that the emulator is not just a simulator. It's actually running the Android virtual machine, so you can test and debug your app on different hardware and software configurations. You can interact with the app on the emulator using the screen or with the navigation controls here. You can also invoke other apps, do network calls, play audio or video, and much more. It also includes debug capabilities, including log output and the ability to simulate app interrupts or network latency. You can also hit home and browse around the device to see other apps. For example, you can check out API demos. Feel free to play around with the emulator some more. If you open up Android Device Monitor, you can go into the Emulator Control tab. There you'll see different options for simulating behavior on your AVD, such as for telephony and for location. Now that the Hello World app runs on the emulator, let's see what goes on behind the scenes to make the app run.
The simplicity of hitting Run and having your app appear on an emulator hides a lot of complexity. Remember that Android is a full software stack. At its base is a Linux kernel, which handles low-level tasks like hardware drivers and power management. On top of that are some core C and C++ libraries like libc and SQLite, and the Android runtime. That includes core Android libraries and the Android virtual machine, Dalvik, or more recently, ART. Your apps run within its own instance of the VM using the classes and services provided here in the application framework. On top of that sits the application layer, which includes your app and every other app that's installed on the device. So when you hit Run in Android Studio, the first thing that happens is your code gets compiled into bytecode that can be run in the Android virtual machine. That then gets installed onto the device. In Android Studio, this is done using Gradle, a build toolkit that manages dependencies and allows you to define custom build logic. You can manually start a Gradle build in the IDE by selecting Make Project. You can also do this by going to the Build menu and selecting Make Project from there. Or you can use the Gradle console to observe any logs or build errors. Or open the Gradle Tasks window to see any available tasks. Double-clicking on any of them will execute it. This all works from the command line too. Once you've navigated to the root of your project folder, you can run Gradle W tasks to see all of the tasks that you can run. You can learn more about Gradle by checking out the links in the instructor notes. For now, note that we start with a project, which Gradle then builds, and then packages the bytecode along with the external resources such as images, strings, and UI XML into an application package. This is called an APK, and it's a specially formatted zip file. Once you've got your APK ready to go, it's signed and then pushed to the device using the Android Debug Bridge, or ADB. If we return to the terminal, you can see that ADB lets you interact and debug apps on any device, physical or virtual, things like pushing and pulling files, viewing logcat output, or even running a remote shell. So once Android Studio has ADB installed the APK, it uses ADB again to launch the app by sending a start command via the remote shell, by identifying the package and class name of your main activity.
Thanks, Rado. And now it's time to install the Sunshine app on our phones. So to get started, let's grab a USB cable. We'll plug in our device, and then we'll need to enable USB debugging. This can be found in Developer Options in the Settings app. But note that on Android devices 4.2 and above, the option is actually hidden by default. To find the secret menu, go to the Settings app. Scroll down to About Phone, then go down to Build Number and tap on that 7 times. Then, when you go back to Settings, you'll see the Developer Options menu appear. Also set up your computer to detect your device. Check the instructor notes for more details. We're going to continue using a device because it's faster and smoother for development. But if you don't have one, that's okay. You can continue using the emulator that we created previously. Now in Android Studio, you can hit the play button to run the app on your device. In the Device Chooser dialog, you should see your connected device. To prevent the dialog from popping up in future times, check this box, then hit OK to continue. Within a few moments, you should see it on your phone. On the other hand, as Rado was mentioning, you can use command line tools. From the root folder of the project, use Gradle W to build your app on Mac or Linux. Check the link in the notes below if you're using Windows. This first command grants execution permission to the Gradle wrapper script, and you only need to do it the first time you're trying to build from the command line. Then you can call Gradle W assemble debug. Once the build is successful, it creates an APK file at the app build APK directory. You can use ADB to install the app. The -r command means that you can replace an existing version of the app if you've already done it before. For more tips on ADB, you can see the instructor notes below. Then you can use this ADB command with the Activity Manager tool in order to start the main activity. And there you see it on the device. And now we see it running on our phones. Woohoo! Fist bump. We're on a roll. Let's go find Dan so that we can build up the Sunshine UI. Woo!
Let's build up the UI for the weather app. We've created our Android project and understand more about basic tools. So let's go to the user interface for Sunshine. Specifically, we're building the initial screen, a list of forecasts for the next several days. Main activity is launched when you start the app. At the bottom of main activity, we have placeholder fragment. Placeholder fragment was generated by the template we used when creating our project. A fragment is a modular container within your activity. In later lessons, we'll look at how to use multiple fragments in a single activity, and we'll actually explain why we're using them at all. But for now, our activity contains just this one fragment. So here in placeholder fragment is where we reference our UI layout resource, called fragment main. This XML file lives in the resources res directory of our project folder. You can see other kinds of resources here besides layouts, such as design assets or drawables, or strings. When our activity runs, it creates this placeholder fragment, which then inflates the XML layout resource, converting everything in the XML file to a hierarchy of view objects in memory. By holding Control or Command, depending on your operating system, and clicking on this reference to fragment main, Android Studio will drop us right into the visual layout editor. Once we're inside a layout XML file, we can switch between the Design tab, where we can drag and drop new UI elements and modify the layout visually, and the Text tab, where we can see and edit the XML that defines the layout and UI elements. All of the views we'll talk about here ultimately extend the view base class. The template we used gives us a relative layout with some padding around the edges. We'll get into layout features like padding and margins later. Inside our relative layout is a single text view that says, Hello World. Edit Text is a text entry field that is an editable version of text view. It has many options, such as whether it supports single or multi-line. There are several styled versions of edit text in the text fields section of Android Studio, such as name, email, phone, or postal address. Each one sets the soft keyboard into an appropriate entry mode. Image View displays the image defined in its source attribute. It has some really useful features, like zooming and cropping if the source image is too large, or has a different aspect ratio than the image view itself. A list view is a special kind of view that contains one or more views that are replicated to display sets of data. In this case, this single text view is used to display the weather information replicated throughout the list. We'll get into much more detail about list views later on. The editor is quite powerful. Without using any code, one can create relatively sophisticated layouts. Make sure to use the built-in styled text widgets for large and medium text. All of the text is just placeholder text, so you can easily enter it using the visual editor. If you're proud of your creation, take a screenshot and post it along with the XML into the forums. Now that you have some background on the basic tools in Android Studio and a few of the basic Android user interface views, Catherine will show you how to start making some sunshine.
Perfect. Thanks, Dan. Since he's turned you into a UI expert now, where should we define this list item layout? If you're thinking the layout folder under the resources directory, then you are correct. Here you can create a new layout resource file called list item forecast. Inside that file, define a text view as the root view. Then assign it an ID list item forecast text view. Give it a minimum height so that the list item isn't too short for tapping on, and vertically center the text within that item. Go ahead and try it yourself now, and check the box when you're done. And here's the solution. You create a new layout resource file, call it list item forecast, and the root element is a text view, and then you just hit OK. Now that we have the item created, we can switch to the text pane. Here's the solution code. We have a single text view where the width is match parent and the height is wrap content. We also give it a minimum height so the item is tappable. We use the framework preferred item height for this. Since there'll be more vertical space now with a minimum height, we specify gravity so that the text inside the text view will be centered vertically. Lastly, we specify ID, which we gave you earlier. Great, now we have a list item.
Imagine spending hours crafting the perfect layout. What happens to that layout when you rotate the device into a landscape orientation, or when it's run on a device with a much larger screen? The good news is that Android provides excellent tools to help you with layouts. You'll want to understand them to make your app look amazing across the wide variety of phones, tablets, and other devices you'll want your app to work on.
Building something that looks great in the visual layout editor is the easy part. You also need to consider different screens and orientations. As you begin to lay out your UI, there's a temptation to build it pixel perfect for the device you happen to be using at the time. This is reinforced by the fact that your app's window doesn't generally change size while it's running. So you can't just grab the lower right corner and grow and shrink your app to see how it behaves. But if you've ever developed for the web or desktop, you know this static approach is a bad idea. When Android first launched, HVGA 480 by 320 resolution screens were standard. As we began exploring how to build engaging user experiences on those devices, we could use absolute layouts to define the exact location of each screen element. But within a year, the first WVGA Android phones were released. And now Android runs on everything from phones to phablets, tablets, TVs, and wearables, with any screen size, resolution, and aspect ratio you could imagine. So, just like desktop or web, where you might use panels or CSS, your Android UI needs to scale based on the screen it's running within, which is why absolute layout was deprecated. In favor of layouts like linear layout, relative layout, and grid layout that can dynamically resize and adapt to any screen following the principles of responsive design.
Responsive design. I know. It's fun to resize your web browser and see which sites resize gracefully and which sides remain defiantly large with gross horizontal scroll bars. But responsive design is not just for the web. Today, the lines between phones and tablets are disappearing, so it's important to think about how your UI will scale in our multi-screen world. Don't be overwhelmed. Just like designing responsive layouts for the web, build your layouts to be reasonably flexible or within a common device size. Then you can set breakpoints, providing alternative layouts for those various sizes. Think about it this way: small phone, large phone, medium tablet, and large tablet. Going back to what Reto said, frame layout, linear layout, and relative layout are three of the most common layouts you'll use in building out your UI. These all descend from the view group class, designed to contain and give order to child views. They each have their strengths, and you should always try to use the simplest layout that will get the job done. Frame layout is great for simple layouts when you only have one child view, like a list view that fills the entire content area. Linear layout is perfect for stacking views vertically or horizontally, one after another. It is also the only way to break up the display proportionately. Relative layout is powerful, but a bit more complicated compared to the others. Throw a bunch of views inside a relative layout, and then you can configure each view's position relative to the parent, the relative layout, or to sibling views. Tons of possibilities. We'll explore these layouts in greater detail when we build more complex screens. For now, let's get back to building our forecast list.
On the surface, creating a list of items is simple enough. Android includes a scroll view, into which you can place a linear layout. That in turn arranges each item it contains into a vertical list. Note the items which have fallen off the bottom of the linear layout and therefore aren't currently visible in our UI. The scroll view, as the name suggests, will let the user scroll through the contents of the layout it contains. But there's a challenge associated with that approach on a device with limited memory and where touch responsiveness is critically important. If you have 50 items in a list and can fit 10 items on screen at any given time, what's the minimum number of views you'd need to create in order to scroll through every item on the list? The answer might not be immediately obvious, but think about ways in which you can be more efficient in your use of the views used to display the entire list. Adding every item to the linear layout within the scroll view means that every view we create sticks around, taking up memory even if it's never been seen. We want to try and create a way that we only need to use as many views as are currently visible in the screen, plus one on either end to make sure we can scroll without flickering. To do that, Android uses ListView, so let's take a closer look at that now. The ListView starts by requesting a view for every visible item, however many it can fit onto the screen. It'll also create a couple in either direction, to make sure that we can scroll without seeing a flicker as a new view is created and populated. Then it creates new items just in time, so it's next in line to be visible to the user. So if the user never scrolls to the bottom of the list, the ListView will never request that view from the adapter. But this is really just a half measure. As you can see, if the user keeps scrolling, we could potentially just keep adding new views, even if they disappear off the top of the screen. Eventually, that's going to lead to the same impact in memory use and performance as if we had just created all of these views directly at the beginning. The solution is recycling each view as it scrolls off the screen, allowing it to be reused when we need to show another item as it moves into view at the top or bottom. So rather than having to create and then hold in memory each item of the list as it comes into view, we only need to do the creation step for the number of visible items and a couple on either side. Then, whenever a new list item comes into view, we just update the data displayed in one of the items in our recycle bin. The result? Less memory overhead, smoother scrolling, and less view management you have to do yourself. This same recycling behavior is implemented across all adaptive view descended classes, such as GridView and ListView, which also introduces the reason that the adapter isn't built directly into these controls themselves. By keeping them separate, your adapter defines how to display each element of the underlying data, while the adaptive view implementation itself is responsible for controlling how each of these elements is laid out, be it a list or a grid in these particular instances.
Thanks, Rado. Now that we know the distinct advantages of using a list view, we can use a list view to display the list of weather forecasts in our app. Now, which file in the layout folder should we modify to accomplish this? Well, we want to add the list view directly to the fragment. If you open up the fragment main XML file, you'll notice that the layout includes a relative layout as a parent view as well as a child text view. Modify this file so that we show a list view instead of a text view, and assign it an ID ListViewForecast so we can reference it later. Also, since this layout only contains one child's view, it would be more efficient to actually switch to a frame layout instead of a relative layout. After you make the changes, compile and run your app. You will be a little bit underwhelmed with the blank screen, but that's okay. That's because we haven't populated the list view with data yet, and that will come in a later step. Check the box when you're done. You should have changed the text view into a list view element. Then you can remove this text attribute because we don't need it anymore. Now from the UX mocks, you'll remember that the list takes up the whole screen, so we want to set the width and height to be match parent. That will make the list view match the dimensions of its parent, which is this relative layout. And to find out the parent of this relative layout, it's actually in this activity main XML file because the fragment is contained within the activity. Within this file, we see that this view is also match parent for height and width, so now we can confirm that the list view actually will take up the full screen. Going back to the fragment main file, we can add the ID list view forecast onto the list view. And then since this layout only contains one child, we can simplify the layout by changing this into a frame layout. With our list view ready to go, we'll want to create some fake data to populate it. Open up mainActivity.java and then scroll down to the bottom where the placeholder fragment class is. Within the onCreateView method, create an array list of strings to represent the weather forecast list items shown in the wireframes. For example, the today list item will be represented as a string shown here. When you're done, check the box and submit. At this point, we should have created some fake data to display in our list. We created an array of strings to represent each weather forecast item, and then we turned it into an array list. Given some sample data, how do we populate a list view? Let's look at an example of some contact data and how it can be displayed in the list. We start with our raw data of contacts, which is 3 contacts as well as their profile images. Then we pass this data into the adapter so it has a reference to it. The adapter also knows how to build a list item layout for each of these data items. So it could go ahead and create the layouts for them. But we don't need to create the views yet until the list view requests that it needs them. For example, if you had hundreds of contacts here, you wouldn't want hundreds of layouts sitting around that aren't being used. Then when you bind the adapter to the list view will ask how many items are actually in the dataset. And the adapter will check that in the dataset there's 3 items, so it will return that to the list view. Now the list view knows that it will have to populate itself with 3 list items. Now the list view starts at position 0 and asks for the list item layout located at that position. It goes back to the adapter, and the adapter checks that at position 0 we have the contact Anna. The adapter knows how to create a list item layout from the contact Anna, so it goes ahead and does that, and then we return it to the list view. And now we see that the Anna list item is located at the 0th position in the list. Next, the list view wants to get the item at position 1, so asks for the layout from the adapter. The adapter checks that at position 1 we have the contact Bob. The adapter knows how to create a list item layout for Bob, so it goes ahead and does that, and then it returns it to the list view. And now we see that the list item for Bob has been successfully added to the list view at position 1. Now the list view fetches its last item, because it knows that there was 3 list items to expect. It fetches the last list item layout at position 2 by asking the adapter. The adapter checks that at position 2 we have Charlie, as well as that image, and we know how to make a list item layout for Charlie, so we can go ahead and do that and then return it to the list view. And now we have the list item for Charlie at position 2 in the list, and we have our complete list. In our code, we're going to initialize the adapter within the placeholder fragment onCreateView method, because that's where we want the list view to be populated with data. We're using an array adapter, and we can initialize it with 4 parameters: a context, the ID of a list item layout, the ID of a text view within that list item layout, as well as the list of data. We'll go through each of these parameters one by one now. First, for context, it contains global information about the app environment. It allows us to access system services and resources, as well as the application-specific resources that we've defined. We use the fragments containing activity as a context, so we're going to call getActivity for our parameter here. Since the adapter needs to know the layout for each list item, it needs some reference to the XML layouts that we've defined. The r.java class is a generated file that creates human-readable identifiers for our resources. For the list item layout, we refer to it in code as r.layout.listItemForecast. This was the name of the XML file that we created earlier. Next, the array adapter needs to know how to take the weather forecast string and set that to be displayed in a text view. so we pass in the ID of the text view that we defined earlier in the list item layout. Even though these two resource IDs look similar, one starts with r.layout while the other starts with r.id. r.layout refers to a layout file, while an ID refers to a specific XML element with the matching ID attribute. And lastly, we pass in week forecast, which is the array list of forecast data that we defined earlier. Now go ahead and initialize your adapter. Check this box when you're done. When you've declared your array adapter of strings, it should look something like this. We pass in the context, which is this fragment's parent activity, as well as the ID of the list item layout, and the ID of the text view we want to populate. And lastly, we pass in the forecast data. Once the adapter is initialized, let's bind it to the list view. But you may notice that we don't have a reference to the list view in our fragment. It was only defined in the layout XML. The system takes and inflates layout XML files and turns them into a full view hierarchy, with the root layout of the main activity at the very top of the view tree. We can also assign IDs to each view in the tree, but it's not required if you don't need a reference to an individual view. For example, this image view doesn't have an ID associated with it, and that's okay. Within the Java code of the associated activity or fragment, if we need a reference to the button, we can simply call findViewById, which will traverse down the view hierarchy until it finds a view with the ID button, and then it will return that. Similarly, we can traverse down the view hierarchy to find the linear layout with the ID container, and then return that. We could do the same to find a reference to this text view by traversing down the view hierarchy, but you'll notice that we already have a reference to the container, which is the direct parent of this text view. Hence, we can just call container.findViewById to search this subtree to find the text view with this ID, and then return it. With this method, we have a smaller subtree to search for a given view, as opposed to searching the entire view hierarchy. In the Android Java doc for the View class, which is linked below if you want to follow along, it contains an example where the button was defined in layout XML. It was assigned an ID myButton. Then, in the activity, we can use the findViewById method with that ID so that we can get a reference to the button. Then we can change it dynamically, such as by adding a click listener to it. Now in the placeholder fragment class, find the adapter to the list view. Luckily, we did assign an ID to the list view earlier, so we can find it easily now. Think about the smallest subtree in the view hierarchy that you can call findViewById on. Then set the adapter on it. If you want an example, you can see one in the link below. Check the boxes when you're done. Here's the solution for binding an adapter to a list view within the placeholder fragment class. First, we find the list view in the view hierarchy by using the findViewById call, and then we set the adapter to it. The adapter will supply list item layouts to the list view based on this week forecast data. Note that the root view here refers to the root view of the fragment, which we just inflated up above here.
And now we have this beautiful list of weather data in our app. Great job! High five!
You've accomplished a lot in this first lesson. Starting with nothing more than Android Studio and hope, you've created your first project, built and deployed it to virtual and actual devices, and even created a simple list-based UI that's populated using an adapter. You also learned a little about what makes mobile, and Android in particular, a different environment to develop for than desktop, web, and server. But we've only just gotten started. The app we've got so far is using static mock data, so join us in Lesson 2 to learn how to hook it up to real weather data. But before that, take a moment to cleanse your palate with a brief interlude exploring the history and evolution of the Android ecosystem. I asked my first Android question on Stack Overflow on August 25th, 2008. It was about a problem I was having on the 0.9 Android Beta SDK. Android has evolved quickly since then, and nowhere is that more apparent than here in the Android Desert Sculpture Garden, at the very heart of Android, Building 44 at Google HQ. More than just a convenient place to take a photo with a life-size sculpture of your favorite dessert, it also tells the history of Android. In terms of food, every Android launch has two things in common: work from work, bacon Sundays and the crunch time leading up to each launch, and a dessert theme codenamed memorialized forever here in the Android Desert Sculpture Garden. Each release brings with it new hardware, APIs and features for developers to play with. The third major Android release, 1.5, or Cupcake as it was codenamed, brought video recording and widgets to the Android SDK, and the first baked good to our front lawn. Android 1.6 and 2.0 brought with them giant donuts and eclairs, as well as support for different screen sizes and tracking multiple simultaneous touchpoints. The biggest challenge for Android 2.2 was coming up with a baked dessert starting with the letter F. A challenge we ultimately ignored, instead introducing this giant bowl of froyo to the neighborhood, along with adding cloud device messaging to the platform. That brings us to Android 2.3 and this giant life-size gingerbread man, along with system support for barometers, gyroscopes and NFC. Android 3.0 was the honeycomb release, the first one targeted specifically for tablets, and paving the way for Android 4.0. Android 4, Ice Cream Sandwich, brought phones and tablets back together. It also introduced Android Beam and everyone's favourite font, Roboto. Android 4.1, Jelly Bean, was the first platform release to feature rich, expandable notifications. It was also the first sculpture to spontaneously combust, thanks to a version 1 design that we've since patented as a solar-powered pressure cooker. But that's another story. Which brings us to the newest member of our team, Android 4.4, KitKat, with sensor batching, host card emulation, and an API for text messaging. So how do the dessert names get decided? Well, ultimately, the only real rule is sequential lettering. Then it's down to intense lobbying, threats, bribery, and centi-threads on the ease of spelling, cultural resonance, and statuability of each proposal. Eventually, something just sort of sticks, but even then we can surprise ourselves. Take a look at the Git history for the K release, and you'll see that even KitKat wasn't always KitKat. As for what comes next, we'll have to wait and see what the next statue is before we know for sure.